Welcome to the Moving Charges and Magnetism Part 1 session with me, your Captain Shreyas. I hope I'm audible and visible. Do let me know in the chat box if I'm visible as well as audible. Welcome aboard, welcome aboard, welcome aboard. Now in today's class, what we are going to see is very interesting. We are going to talk about what is magnetic field, how do charges move inside magnetic field, does a wire which carries current, will that experience force? What about a coil which is carrying current, will it experience some force or some kind of a torque, right? And what if there is electric field and magnetic field both together? And then finally, based on all these principles, we will see how a galvanometer is basically constructed. I hope this is clear. Yep, no problem. Godwin, I'm so glad you came here to tell that, and I like your sincerity. Thank you so much. Hello Salit, hello Srinath, Dr. Asta, good evening. Hello Darshan, Sangeeta, India, Priyanka, welcome Prabha, welcome Kirtana. Nice to see all of you. So get excited, get ready, get set, go, because we are going to cover all these topics highlighted. In part 2, we will be doing these topics which are not highlighted, which is basically sources of magnetic field. Actually speaking, this chapter can be divided into two parts. First part is what does a magnetic field do? And then we talk about how does that magnetic field come. So those are basically the two parts. Today we are studying what does a magnetic field do? That is the effects of the magnetic field. Where does it come from? That we will be studying in the part 2. I hope that is clear, and you guys have smashed the like button. If you haven't, do that right now. If you have not yet joined the Telegram channel, join it right now, because that's where you are going to get the PDF. If you have not yet subscribed to the channel, what are you waiting for? You will miss the next class, right? And if you are not getting your friends here, I will be forced to stop this series. So I want each and every one of you with full sincerity, not just attend the classes, but also talk about the channel, talk about the videos, attend the classes as much as possible live, if not recorded. But I want every student in the country who is studying in English medium should attend this particular channel. This is the only NEET English channel in the country. And this is the English channel in the country, the NEET channel in the country, which is, I think, better than many of the Hindi channels out there. So I want to make sure that there are many doctors which will come out from this channel, just like we did last year or this 2023. All right. So let's begin with the following topics: motion in a magnetic field, then this, then this, then this one. All right. So let's start with what is exactly magnetic field, right? Now, the moment I talk about magnetic field, the first thing that comes to your mind is Earth's magnetic field. Or you might have taken a bar magnet in school and you would have played with it, and maybe in the science lab, and you put some iron fillings on a transparent paper or almost translucent paper to see how, you know, the magnetic field lines arrange. You tap them, you will see the magnetic field lines arrange, the iron fillings arrange in a peculiar manner, just like this, just like this. Have you seen that? So obviously these objects like this bar magnet or the earth, they create something around it. That's something which can attract other magnets, can repel other magnets, can apply forces on magnetic objects. That is your magnetic field. So magnetic field is nothing but, you know, it's like the electric field where you feel the presence of a magnet. You feel the presence of the magnetic properties, and because of which there can be attractive or even repulsive forces. Earth produces magnetic field, bar magnet produces magnetic field, a coil which carries current produces magnetic field, your TV has a magnetic field, your mobile phone produces magnetic field, right? So many things can produce, can accept, or they have some magnetic field within or outside of them. So this chapter lays the foundation of many branches, many things of physics, because this is where you study magnetic field. Is that right? Everyone with me? Awesome. Now, to talk more about this particular magnetic field, There are some very interesting things. The symbol for that is B. B is basically the magnetic field. Sometimes it is also called as magnetic induction, or sometimes it is just called as the magnetic field strength. All of them mean the same thing, exactly the same thing. Whenever we talk about magnetic field, remember it is a vector quantity, it will have some direction. So if there is a magnetic field line like this, if this is your field line, then if I take any point on this, then if I draw a tangent, that tangent gives me the direction of the magnetic field. So magnetic field is always tangential to the magnetic field line. Agree or disagree? Everyone with me? Then that means one more thing. That also means one more thing. Just like in electric field, can two electric field lines ever intersect? No, right? This is not possible. Same thing, if this is a magnetic field line, this is another magnetic field line, this cannot happen. So basically field lines can't intersect each other. Is that right? They cannot intersect each other, because then that will create ambiguity, confusion. Is the field here or here? Only one direction is possible. It can't have two directions. I can't say you are let's say an Indian also, you are an American also. Either you are in India or you are in America. You are an Indian or an American. You can't be both. Right? So that's how it is. So it can't have two directions. That's the logic behind it. Another important thing, if the magnetic fields go like this, they are not parallel to each other, they are diverging or converging. Wherever they are crowded, the field is basically stronger. Wherever they are far away, the field is basically weak. So that is a weak field, this is a strong field. It depends on how much is the spacing between them. Exactly like electric field. Everybody agrees with this point? Very good. Next important thing. If I say that the magnetic field lines are like this, what is so speciality about these? All the lines are parallel. That means the strength here, everywhere is same. So can I say this is nothing but uniform field? My dear warriors. Isn't this an uniform field? Very good. Next, if I say that no, the field lines are like this, then maybe like this, this is obviously non-uniform field. This is basically non-uniform field. Even this one, something like this, let's say the field lines are coming this way, this is also non-uniform field, right? Now these are exactly very similar properties like you have studied in electrostatics. Strength is more, strength is less, uniform field, non-uniform field, field lines do not intersect each other, the tangent drawn shows the direction of the field. Looks very similar. But there is one particular thing about field, magnetic field, which is completely different from electric field. How many of you know that? There is one particular thing which is completely different for a magnetic field as compared to the electric field, and that is this one. If you take a magnetic field, it starts somewhere and it ends back at the same point, meaning magnetic field lines are always in a closed loop. So they are magnetic field lines, are always in a closed loop. It can never start or end anywhere. It can't start and end at two different places. If it starts somewhere, it ends at the same point. Basically, there is no start or no end. You can take any point as the start, any point as the end. Yes, they always complete the loop. But electric field lines, we know that if you take a positive charge, they start from the positive charge. If you take a negative charge, they end over here. So that is different. In electric field originates as well as terminates. Originates as well as terminates at different points, but magnetic field cannot do that. Is that right? Everybody with me? Understood? This is one major difference. This is one major difference between magnetic field and electric field. Keep this in mind, my dear students. Very, very important. Talking about the unit of magnetic field. Talking about the unit of magnetic field. What is the unit of magnetic field? The unit of magnetic field in SI is basically Tesla. Tesla, that same company that you are well aware of, making, very nice electric cars by Elon Musk, right? So Tesla. So the short form of that is basically capital T. Is basically capital T. There is one more unit. Very rarely it is used. Very rarely. And that is basically Gauss. And one Gauss is basically 10 to the power minus 4 Tesla. So this Gauss is also an unit of magnetic field, but it is a very small unit. When you take a bar magnet, do you know how much is the magnetic field around it? Do you know how much is the magnetic field roughly around Earth on the surface? It is very small. It is 10 to the power minus 4. So the Earth's magnetic field on the surface is close to 10 to the power minus 4 approximately. 10 to the power minus 4 what? Tesla. Basically one Gauss. If you go around a bar magnet, the magnetic field is close to approximately 10 to the power minus 2 Tesla. Meaning 0.01 Tesla, around that range. That's the order of the field if you take a bar magnet. So don't expect 1, 2 Teslas or 100 Teslas of magnetic field normally around you. 100 Tesla, 200 Tesla magnetic field is crazy magnetic field. In fact, you would have heard about MRI machines, CT scans. Have you heard about that? Come on, you guys are the future doctors. You would have definitely heard about this. What do they tell when you go for an MRI scan? What do they tell? Remove the ornaments. If you have some metallic things like the watch or chain or whatever jewelry, remove that, right? That's what they tell. Why do they tell that? Because there is a magnetic field in which you enter, and that magnetic field is analyzed to detect any abnormality in the body. That magnetic field is around 2 to 3 Teslas. How much? 2 to 3 Teslas. That 2 to 3 Teslas is enough to rip apart. If you are wearing a watch, it will rip apart from your hand. It will not stay there. If you are wearing a jewelry, that's it. It will cut your neck. If you are wearing a metallic bangle, it will cut your hand and it will come out. That's how strong that magnetic field is. So imagine 100, 200 Teslas is like unimaginable actually. Okay, so that is the order of the magnetic field that you should understand. Is that clear? Very good. So now that we know everything about how magnetic field works, what's the direction, what's the meaning of uniform, non-uniform magnetic field, and the difference between electric field and magnetic field. Magnetic field is in loops, electric field is not in loops. It starts and ends somewhere. Will this magnetic field apply forces on charges? So there were experiments which were conducted, something like this. Imagine you take a magnetic field this way. This is basically, let's say for example, the magnetic field. This is the magnetic field. Then they took charges. They took a charge, let's say charge Q, okay, charge Q, again charge Q, and again charge Q. They performed certain experiments, like they just kept this charge at rest in this case. This charge, they made it move in this particular direction with some velocity. In this case, they made it move in this direction with some velocity. In this case, they made it move perpendicular, let's say like this. And they saw how it gets deflected, how it moves. So this was purely experimental. And what they found was very interesting. This is what they found. In the first case, when the charge is at rest, there was actually no force. There was no force on it. Basically, it remained at rest. Nothing happened. You keep a charge inside magnetic field, nothing will happen. It will stay there. Nothing will happen. It will stay there. Everybody fine till this point? Okay. Now, the next setup, what they did, they moved the charge parallel to the magnetic field. They threw the charge in the magnetic field parallel to it. They saw neither the speed increased nor the speed decreased. Neither the charge moved this way nor that way. It kept going in a straight line with constant speed, means no force on it. So there was no force on it only. They're like, okay, nothing happening. They moved it opposite to the field. Still they found there was no force acting on it. Then they were like, oh my God, I keep it as it is, nothing happens. I throw it like this, nothing happens. I throw it opposite, nothing happens. What if I throw it like that? What if I throw it basically like that, perpendicular? Then they saw force was not zero. In fact, the force came inside the plane. The force acting on the charge was like this. This force was not zero. Then they understood, oh, wait a minute. Whenever I give velocity, the velocity which is along the magnetic field does not affect the charge, does not create any force. But the velocity which is perpendicular to the magnetic field, that creates the force, and that force is perpendicular to both velocity and magnetic field. When I show a cross, that means it's a vector going inside the plane of the board, away from you. It's going away from you, inside the plane of the board. Understand that. If I showed a dot, that means it is coming out of the plane towards you. If it's a dot, it's a vector coming towards you. If it's a cross, it's a vector going inside the plane. Are you able to visualize this? This is like y-axis, x-axis, z-axis, something like that. Right, very good. So this made them conclude finally the statement, like if you have magnetic field and if you take a charge q and you throw it at some angle like this, there will be two components. One will be v cos theta, the other component will be like this, which will be v sin theta, and there will be force acting on it. The force acting will be like this. There will be a force acting on it like this. That force will only depend on v sin theta, v cos theta. This particular v cos theta will not be generating any force. It's a useless component. Only v sin theta is the useful component. And this force was found to be directly proportional to the velocities sin theta, that means the perpendicular component. It was also found out to be proportional to the charge. And it was also found out to be proportional to the magnetic field. So therefore, in SI units, I can just write it as F is equal to, I replace the proportionality with a constant which is 1 in SI units, and I define it like this. I put charge over here, I put V sin theta over here, and then I put magnetic field over here. The moment I see this equation, you should quickly be reminded of a peculiar vector operation. There is a vector here, there is a vector here. They both are multiplied with the sine of the angle between them to give you another vector, which is perpendicular to both this vector as well as this vector. You have studied that vector operation. When you multiply two vectors as a cross product, A cross B is C. C is perpendicular to both this as this and this, and the magnitude is, basically A B sin theta. It's exactly that. So hence, I can just write this as the force is equal to, charge is a scalar, please remember, charge is a scalar, just leave it outside. You just put V and then put cross, and then put the magnetic field V cross B. If you want, you can also put this like this, that's okay. You can do V cross B first, then multiply by the charge, you get the force. So that is the vector quantity over here, vector equation. Very, very important equation, my dear students. Very, very important equation. Interesting thing to note is because the force is perpendicular. The force is perpendicular to both the velocity as well as the magnetic field. The velocity as well as the magnetic field. Keep this in mind because it is a vector cross product. It's a vector cross product. So therefore this force will be perpendicular to both velocity as well as the magnetic field. Keep this in mind. This also means once the force is perpendicular to the velocity, it also means that the work done by that force will always be zero. The power delivered by the force will also be zero. Because whenever force and displacement are perpendicular, there is no work done. Perpendicular force never does work. Keep that in mind. Right? So very, very important. Exactly. Is that understood, my dear warriors? Everyone till this point? Okay. Now remember, this Q has to be put with the sign. Has to be put with the sign. If you change the sign, then the force will change the direction. Let's take some examples so that you understand it. Let's take certain examples. Imagine that there is a positive charge. Let's say it is going like this. Let's say the magnetic field is maybe like this. Magnetic field is like this. Let's say I take a negative charge. Let's say the velocity is like this. Let's say the magnetic field is like this. Let's say I take again a positive charge. Maybe it is going like this velocity, and let's say the magnetic field is inside the plane of the board. Inside the plane of the board. Okay. Let's take a negative charge, and let's say the velocity is this way, and magnetic field is coming towards you. Magnetic field is coming towards you. So I've just taken few cases, my dear students, and in each case I want to figure out what is the direction of the force. Every time the same equation I'm going to use, and the equation which I'm going to use is F is equal to Q into V cross B. This is the standard equation which I will have to use. Let's do the cross product. Everybody take out your right hand. Take out your right hand, everyone, right? If you're using a phone, hope so you are holding it in your left hand, right? So V cross B, if you do V, take your right hand, put it like this, and slowly move it towards B. When you do V cross B, where is the thumb coming? Into your mouth? It's coming in your mouth, yes or no? Don't lick your thumb now. It's not going away from you, no? V cross B, see if the thumb is coming towards you. That is the direction of the force. That is the direction of the force. So can I say the force is basically towards you? And I can see that the charge is positive. So positive means whatever that direction is, it is correct. It is the same direction. Do over here. V cross B, again the same thing. V cross B, the thumb will come inside your mouth, basically out of the plane. But there is a negative charge. So the moment you multiply with a minus sign, the vector coming towards you is negated, so that vector will go inside the plane of the board. So can I say that the force acting will be in this particular direction? The force acting will be inside the plane. Exactly, everyone with me? Understood? So again, V cross B towards you, but it's a positive charge, so the direction is correct. V cross B towards you, but it's a negative charge, so flip the direction. So it is inside, that's why the cross. Let's talk about this. Be a little bit careful. Velocity is down, magnetic field is inside. Velocity is down, magnetic field is inside. So stand like this. Take your right hand like this, and bend your right hand like this, and point it downwards. First hold your right hand just normally like this, then point all the four fingers downwards in the direction of velocity, and slowly bring it forward towards the front of you in the direction of magnetic field. Do you see the thumb going towards the right side? Velocity is downwards, magnetic field, it will come in front of you, right? V cross B. See if the thumb is going towards the right side. towards your right side. That's where the thumb should go. Just try it out. Yep. So I think because this is positive charge, the force should be in this particular direction. See if everyone is getting it. Everybody is getting it. Perfecto. What about this? Velocity is left side, magnetic field is towards you. Velocity is left side, magnetic field is coming towards you. So if you're standing like this, just take your right hand and take it here. Take your right hand and bring it on the left side. Bring your right hand on the left side. It's pointing in the direction of the velocity towards the left. And then slowly bring it behind you. Slowly bring those 4 fingers behind you, because that's where the magnetic field is. Velocity is there, magnetic field is behind you. See where the thumb is going. See where the thumb is going. Upwards. V cross B is upwards. But you will not take the upward direction. Why? Because it's negative. It is negative charge. So bring it down. So hence the force will be downwards. Hence the force will be downwards. Understood how to do this? Yep. Very good. Perfecto. Understood how to get the direction. Everybody is clear in their head. Everybody is clear in their head. Awesomeness. Now let's take some special cases. Some special cases where magnetic field is there, velocity is there, and what happens? Obviously, we won't take these cases where velocity is anti-parallel or parallel, because I know force will be 0, so nothing will happen. It will just go in a straight line. We will take some peculiar cases where velocity is perpendicular or making an angle. So that's when the force will not be 0. So let's take some very peculiar cases. So case one, where you have transverse. Transverse means perpendicular. Transverse magnetic field. Transverse magnetic field. What does it mean? Observe now. Imagine the magnetic field is, let's say, inside the plane of your board. Inside the plane of your board, like this. So these crosses show that the magnetic field is basically inside. It is inside the plane of the board. Okay, it's there everywhere. Now let's say, for example, you throw a particle perpendicular to the field. B is inside, magnetic field is inside, perpendicular to that. B is inside, perpendicular to that. So essentially you are just throwing the particle like this. You're just throwing the particle like this with some velocity. There is a charge Q. Can you guess the direction of the force? Everyone put up the answer in the chat box. I'm reading your chats. I'm reading your chats. Come on, tell me. Where do you think is the magnetic force? Use the formula. Same formula. V cross B into charge. Assume the charge is positive. So velocity first. Okay, I'll stand like this. Velocity is there. So take your right hand like this. Point it in the direction of the velocity. Point it in the direction of velocity. Magnetic field is inside. So slowly bend your fingers. Slowly bend your fingers inside. You will see the thumb going up. You will see the thumb going up. So that means the magnetic force is in this particular direction. The magnetic force is in this particular direction. Everyone with me? Awesome. Very good, Dr. Asta. Friends forever, Abinya. Very good, Naveen. Very good. Don't compromise. Awesomeness. Very good. Very good. You guys are enjoying. Keep it up. I want you to enjoy and learn a lot. Awesome. Trust me, after today's class, you don't have to attend any class to understand this topic. I'm going to complete the syllabus very soon, before you even realize. And after that, we'll have PYQ sessions, mock tests, practice sessions, so many things, revisions, final lab, mind maps, everything are planned. Right? So for that, first we need to complete the syllabus, and stay with me, guys. That's why I need your support. Keep smashing the like button, and also make sure you are subscribed. Get your friends also on the channel. Okay. Now, once this force is acting, velocity is like this, it will move forward, but it will turn. It will move forward, but it will turn slightly. Maybe it will go like this. Maybe it will turn like this. Once it reaches there, where will the force be? The force will be perpendicular to that velocity. The force will be perpendicular to that velocity. So that means the velocity will turn even further. Always it is going to be perpendicular. So think about it. Again, when it reaches here, the force will be perpendicular to it. Force will be perpendicular to it. So it will keep turning, keep turning. Basically, it is going in a circular path I hope you realize basically it is going in a circular path like this, isn't it? Is it not going in a circular path? Everyone with me? Yes, friends, forever. It is going in a circular motion. Perfect. So this is uniform circular motion or non-uniform circular motion? Uniform circular motion or non-uniform circular motion? The speed will never change. Direction changes. That's okay. When speed is constant, what is it called? Uniform circular motion. So basically it performs what? Uniform circular motion. Uniform circular motion. The V's magnitude is always going to remain constant. The direction continuously changes. You will see at every point it is perpendicular to the force. That force acts like the centripetal force. That force acts like the centripetal force. So the centripetal force will be F, and that is always m into AC. AC, centripetal acceleration, is velocity square by the radius. The force is charge into velocity into magnetic field into sine 90. Why sine 90? Because angle between velocity and magnetic field, transverse means 90 degrees. So this is what you will get. QVB sine 90 is mv square by r. Do you see v and v gets cancelled? So can I say Q into B is equal to mv by r? So then can I say R is equal to m times v divided by QB, or you can also say it is momentum by QB, one and the same thing. Now this formula is very important. You should know this, because you can get direct questions on the same. You can get direct questions. The radius of the circular path is mass times the speed divided by the charge into the magnetic field. That's the formula. Exactly. Very, very important. Let me tell you, you don't have cyclotron and all that for NEET syllabus. So even if it is there somewhere in your random book or some even coaching module, ignore that. Cyclotron is not there in NEET syllabus. Okay. So don't worry about it. Now the next point that we have to discuss is what is the time period? How much is the time period of the motion? So for the time period, what we will do, time period is nothing but 2 pi r, which is the circumference divided by the speed. Agree or disagree? 2 pi r by that speed. Circumference is the distance by the speed. Time is distance by that speed with which you are traveling. Correct? Perfect. I know r is mv by qb. So why not substitute it over here? So 2 pi by v as it is. Take r from here, which is nothing but mv divided by qb. V cancels, so you will see it is 2 pi m divided by the charge into the magnetic field. That is your time period. Now this formula is also very important, of course. And the interesting part about this formula is it is independent of the speed. Very, very interesting. It is just independent of the speed. Think about it. Crazy, right? It is independent of the speed. Even if you throw it very hard, it will still take the same time. It might go in a big radius, but it will still take the same time to complete the circular motion. Yeah, if you throw it very fast, the radius will be higher, but the time will be the same. That's the interesting part about this. Is that right? Everyone with me? Awesome. Keep these formulas in mind. If I just give you a simple problem on this, if an alpha particle and let's say a proton are projected with same speed in transverse magnetic field, then what is the ratio of the radius of alpha particle upon proton, and what is the ratio of the time period of the alpha particle upon time period of the proton? These are the two things that have been asked. These are the two things which have been asked. All right, so let's think, how do we solve this particular problem? Alpha particle and proton, if you notice, their masses are different, even their charges are different. Masses and charges both are going to be different. Okay, if you talk about the radius, radius is mass times velocity divided by q into b. It's being thrown in the same magnetic field, it is being thrown with the same speed, so v and b are same, v and b are same. So that means, can I say radius is directly proportional to mass divided by charge? So radius of alpha upon radius of proton will be mass of alpha by mass of proton, and charge of alpha will be below and charge of the proton will be on the top. Charge of the proton will be on the top. Think, how many times is the mass of the alpha particle as compared to a proton? Protons is nothing but just single proton. Alpha particle means 2 protons, 2 neutrons. 2 protons, 2 neutrons, right? It's a doubly ionized helium nucleus. So basically 4 times the mass of the proton. So can I say there is 4 over here? This is 4 times of this. Everyone with me? This is 4 times of this, the denominator. And if you talk about the charge, charge of a proton is plus e, charge of an alpha particle is plus 2e. So basically the alpha particle is twice as charged as the proton. Okay, mass is 4 times but charge is 2 times. So how much does this come out to be? It basically comes out to be 2:1. So 2:1 is the answer for the first question. Everyone with me? Awesome. Now let's talk about the time periods. Let's basically talk about the time periods. Time period is nothing but 2 pi m by qb. So you can see time period is basically proportional to mass by charge, because b and 2 pi are same for both of them. So time period of alpha by time period of proton will be mass of alpha upon mass of proton, and here you will have charge of alpha and charge of proton. Mass of alpha particle is how many times the mass of the proton? It is 4 times again. Charge of alpha is 2e, charge of proton is e. So it is basically 2 times that of the proton's charge. Alpha particle is 2 times charge as the proton. So again this is coming out to be 2:1 only. Are you getting 2:1? Yep, very good. So both the answers are 2:1. Both the answers came out to be 2:1. Very nice. Let's go and see one more question. Let's go see one more question. Imagine that it is given that there is a charged particle of some charge q and mass m, and it is thrown with some velocity, let's say v. Now there is no magnetic field here, but suddenly the magnetic field comes into play after this point. There is magnetic field after this particular point, like this. Okay, there is magnetic field, imagine. Now this magnetic field is uniform, it is inside, let's say, and it is only present for certain width. It is only present for certain width. Once this charged particle enters inside, it will start turning, it will start deflecting, agree? Till this point it will not deflect. Till this point it will not deflect, it will go straight, nothing is there. Once it enters the field, it will deflect. Now the question is, if I call this as zone 1, this as zone 2 and this as zone 3, I want that the particle should never enter zone 3. Then what is the width? What is the width of that magnetic field? Crazy question. You might be thinking, oh my god sir, what to do in this case? Don't worry, we'll figure it out. First of all, try to visualize what exactly might happen. Just imagine, once the charged particle enters, velocity is there, magnetic field is inside. Velocity is there, magnetic field is inside. So if you do V cross B, if you do velocity cross B, V cross B will be the force this way. So it will deflect like this. It will 100% deflect upwards. So imagine if this is the region where the magnetic field is present. This is the region where the magnetic field is present. The charged particle enters and deflects like this. Oh, it will definitely enters zone 3, 100%. But if this happens, look at this. This is the magnetic field region. Okay. This happens. It enters like this, turns inside, and it comes back. Is that right? This is also possible. It turns, semicircle, and once it comes over here, it will just return back from this side, right? Is that right, everyone with me? Now, the problem is this width will be slightly higher. This is very small. This is too much because there is some extra width which is not necessary. The question is, what is the minimum width which I will need? What is the minimum width which I will need? So think about it. When I will need minimum width, what will happen is the charge particle will enter, turn like this. Maybe I should show it here. Yeah, the charge particle will enter and it will basically turn like this, and it will, wait, I'll just draw the motion first, then I will draw this. Yeah, exactly. So it enters over here and it ends over here, right? So it just grazes through this. It just grazes through this. So this will be that width. This will be that width. And can you guess what is this distance? None other than the radius of the orbit. None other than the radius of that semicircular path. And what is that radius? We already know the formula for the radius. Radius is nothing but mv by qb. So therefore the width must be more than or equal to mv by qb. If it is more than, it's safe. If it is less than, it will go to the other side. If it is exactly equal to, it will just graze through it and come back. It will just graze through it and come back. Is that right? Understood, my dear warriors? Perfecto? Awesome. If I ask you how much time does it spend over here? How much time does it spend over here? Let's say that is also asked. Time spent in the field. Let's say even that is asked. What will you do? How much time will it spend inside the field? It will not spend one complete motion. It will not spend one complete circular motion's time, but it is semicircle. That means exactly half the time. So can I say the time spent is the time period by 2? So it is 2 pi m by qb into half. So 2 will get cancelled. So time period will be pi m by qb. So that's the time which it spends inside the magnetic field, because it is a semicircle. So this half is very important. Exactly. Very good, Priyanka. Very good, Naveen. Perfecto. Don't compromise. Awesomeness. So this is a very good question, and you're slowly learning how to solve the problems. Okay. We'll take the second case now, and after that we'll solve problems. I will give you PYQs, everything will be there. Okay. So let's take the second case. So first case is done. Transverse magnetic field. Let's talk about the second case. Case 2. Case 2. Velocity is at an angle with respect to the field. Velocity is at an angle with respect to the field, meaning it looks something like this. If this is your magnetic field, this is your magnetic field, your velocity over here is, let's say, like this. This is how your velocity is. Now there are two components, like we all know, right? There will be one v cos theta component, and there will be another component like this. This will be the v sine theta component. This is theta. Out of these two, v cos theta will never ever change. It will keep on moving with a constant speed because it does not experience force. So I can just say v cos theta remains constant as there is no magnetic force, as there is no force by the magnetic field, right? Everyone agrees with this? But v sine theta is perpendicular to B. V sine theta is perpendicular to B. And we just studied what happens when there is velocity perpendicular to the field. What happens? Put it up in the chat box. What happens? Thank you, Rani. what happens when the velocity is perpendicular to the magnetic field? I just showed it to you right over here. The moment it is perpendicular, transverse, the velocity is perpendicular to the field, it goes in a circular path. Uniform circular motion, right? This is what I told. It performs uniform circular motion. So the same thing will happen over here also. But you have to think, how will the force be? Well, at this instant, velocity is up. V sine theta is up. Magnetic field is there. V sine theta up. B is there. I think the force, the thumb should go inside. V is up. Magnetic field is right. The thumb goes inside. So the magnetic force at this particular point is inside. So think about it. It will go in a circular motion, but like this. Visualize this. It is perpendicular to the plane of the screen. It's perpendicular to the plane of the screen. Velocity sine theta is here. Magnetic field is here. Force is inwards. So that force will turn that velocity like that. The force will turn the velocity like that. So that velocity will go like this and come out. It will go like this inside and come towards you and go out. Is that, are you able to visualize that? Are you able to visualize that? Everyone, just see this. If you want, I will probably draw a diagram in 3 dimensions for you. So there will be V sine theta like this, and it will basically go like that and come over here. It will go like that and come over here. And this is the direction of your V cos theta. This is the direction of your V cos theta. See if this is clear. Now think both of them are present together. V sine theta is also there, V cos theta is there. Because of V sine theta, it is doing uniform circular motion. Because of V cos theta, it is doing straight line motion. Straight line motion, it is going like this straight. Because of V sine, it is going circular. If both the things happen together, imagine the particle is going round and round, round and round, but also it's going in the front. Also it is going in the front. Can you visualize how is that motion going to be? Crazy. Come on, visualize. It is going round and round, but also it's going in the front. It looks like the coil of a spring. It looks like the coil of your spring. Are you able to visualize that? Are you able to visualize that? Come on, my dear students. So the motion will probably look like this. It will look like this. It will go front, but it will also go round. This kind of motion is called as helical motion. It is called as helix. The motion is called helical. It's like a spring, the shape of a spring. Exactly, that is called helical motion. Nani, we have almost done with the basic maths, whatever is required. Okay, so you can watch the previous basic math classes. That would be sufficient. And also in the Avenger Energized batch, whatever lectures I have done is more than sufficient for NEET level. Okay, I've done graphs, I've done derivatives, integration, trigonometry, all those things. So that is more than sufficient. So this is helical motion. Now when you talk about a helix, there is a very interesting quality of a helix. So both of them together basically gives you this motion, spring-like motion. So if you start at a point, when you complete basically, all right, one rotation. Okay, when you basically complete one rotation, just imagine over here, again you complete one rotation over here, again you complete one rotation over here. Between any such 2 points, that distance is called as the pitch. What is that distance called? It is called as the pitch. After one rotation, how much do you move? Like in a screw. Have you ever tightened a screw or a bottle cap? What happens when you rotate it once? It goes down or comes up. When you rotate it once, either you tighten it or loosen it. So it goes forward. So in one rotation, how much does it go ahead? That is basically called as the pitch. Very simple. It is very simple. Okay. Now we can find this pitch out. It is not that difficult. But first, can you guys quickly think and tell me, for that circular motion, what will be the radius? What will be the radius, or what will be the radius of that helix? That helix will definitely have certain radius. It will definitely have certain radius. Can you guys quickly think and tell me what shall be the radius? Instead of mv, it will be mv sine theta divided by qb. Why V sine theta? Because V sine theta is responsible for the circular motion, that perpendicular component. So that's why only V sine theta will come. No V cos theta, it will be V sine theta. Keep this in mind. Very good. If I ask you the time is not dependent on the speed. The time is nothing but 2 pi m divided by QB. Standard formula, 2 pi m divided by QB. Let's talk about the pitch. Can you guys quickly guess what the pitch could be? How much does it go in one time period? It's going with a constant speed of V cos. It's going with a constant speed of V cos. So obviously V cos theta will be there. That's the speed into the time. Speed into basically the time. The time is basically the time period. What you find over here. That's it. That's the value of the pitch. As simple as that. So you should remember this formula, obviously. Okay, this and this you already know. This is very obvious that you will only take the perpendicular component, because only that perpendicular component will perform uniform circular motion. So that V will be V sine theta. Time is independent of speed, so don't need to worry. Pitch is V cos theta into T. That's it. As simple as that. Everyone with me? Everybody with me on this? Pakka? Understood or clear? Time into speed will be distance. So time into speed will be distance. Meters per second into seconds will be meters. Keep that in mind, right? Not divided by. Awesome. So these kind of questions can definitely come. They will ask you to find the pitch. Like for example, they might give you a question. Like say for example, a charge of, let's say, 5 millicoulomb, all right, with a speed of, example, 10 meters per second, okay, at an angle of 30 degrees with let's say 1 Tesla. If it is thrown, then they ask you what is the pitch. Then they ask you what is the pitch of that particular motion, because it is thrown at an angle. You can clearly see it will definitely have some pitch. Let's say the mass is, let's say, 1 kg. Let's say the mass is 1 kg. So in order to find the pitch, what we need is V cos theta, and I need to multiply it by the time period. V cos theta time period is nothing but 2 pi m by QB. Now you start substituting everything. Velocity is given to be 10. Cos of basically 30. So cos of basically 30 into 2 into pi into mass. Mass is basically 1 kg divided by charge into field. Charge is 5 millicoulomb. So 5 into 10 to the power minus 3. Magnetic field is 1 Tesla. Right? So that's where you go, and you can see many things will get cancelled, like this 5 and this 10 will become 2. So this 2, cos 30 is basically root 3 divided by 2. This 2 and this 2 will also get cancelled. So I think I'm just left with 2 and this root 3 over here, and pi also is also over here on the top. 10 to the power minus 3 will go on the top over here. That's the answer. 2 root 3 pi into 10 to the power 3. That's it. Perfecto. Is that clear, everyone? Understood? That's how you find the pitch of a helical motion when a charge is thrown at an angle. So I think now we should solve some questions. Here are the questions. Gear up. I want everybody fully energized and start answering in the comments in the chats, right? Start it, guys. Come on. The charge is going up, not north, up, vertically up. Magnetic field is towards the north. So visualize, the charge is going up, north is here, okay? Where will the force be? Come on, everyone should answer. I want everybody's spam in the chat box right away, right now. Where will the force be? Come on, think about it. Up, down, left, right, north, west, south, east. Come on, think about it. If the speed is upwards and the magnetic field is in the north direction, that means let's say it is inside. Then if you do V cross B, velocity is up, magnetic field is in front of you, you will see the thumb goes towards the left side. Basically the thumb goes towards the left side. That is the direction of the force. It's a positive charge, so good. Now if you notice, that this is basically your east direction, this is basically your west direction, basically inside that was your north direction, and outside was basically your south direction. That's how it was. This was your up direction and this was your down direction. So clearly it is towards the west. Option C is the correct answer. Option C. Very good, PG Vijay, Sai Priya, Pravina, Chitty, very good, Vidanjini. Thank you for spamming, Pravina, very good. Oscillation is not yet over. No, it's not South Harshan. Yes, GLG, it is towards the left side, towards the west. Correcto, perfecto. Yes, Harshan. Moving on to the next question on your screen now. Charge is -2 microcoulomb. Magnetic field is 2 Tesla. It is in the y direction, okay? The velocity is this much. What is the force? Some newtons in y minus z, z. So directions are also given, magnitude is also given. So the first thing that I shall do is convert the magnetic field in I, j, k component. So the magnetic field technically is in positive j. So it is 2 j cap Tesla. Velocity is already given, charge is also given. So the force will be Q into V cross B. First take care of V cross B, then multiply it with the charge. Charge is 2 micro. Velocity is basically 2 I cap plus 3 j cap. 10 to the power 6 is there, I'll put it later on, into 2 j cap, and there is 10 to the power 6 over here. Now this micro and 10 to the power 6. Micro is 10 to the power minus 6. This is 10 to the power plus 6. They will cancel. So I'm just left with -2. And over here, 2i cross 2j. 2i cross 2j plus 3j cross 2j. We know I cross I is 0. J cross j is also 0. So this term will vanish. I am just left with -2 into 2i into 2j. 2i into 2j is 2 2s are 4. I into j is k. So basically it will be 4k cap. So this will be -8k hat. What is it? Newton. So -8k hat, that means 8 Newton in the negative z direction. Yes, option A for Ames. A for Ames. That's the correct answer. So you had to be very careful with the vector product over here. I'll repeat once again. Velocity, I know. Magnetic field, I figured out, it is given in y-axis, so it is +2 j cap. So I just substituted the values. I saw 10 to the power 6 and micro got cancelled. I multiplied this with this and this with this. J into j is 0, but this I cross j will be k cap. Magnitude wise it is 2 into 2, which is 4. 4 into -2 is -8. That's all. That's the answer. Okay, very straightforward. Go proper via method. Next question is on your screen. Particle goes in a mass m, charge goes, is moving with some speed, circular path, radius r. There is a magnetic field perpendicular. Transverse means perpendicular. What is the work done by the field when it completes one full circle? Very simple. I think everybody should be able to answer this. Every person will be able to answer this, even if you are attending this class very lightly. Sleeping also, if you are holding the phone and you are watching this class, you will be able to answer this. I just told you about the magnetic force. How it acts. If the velocity is like this, and if the magnetic field is like this, right? This is the angle between them. This is perpendicular, and even it is perpendicular to this. Force is always perpendicular to velocity. Work done is always 0. Always. Exactly. Answer should be B. Very good. Excellent. See, everybody knows this answer. Awesome. Keep it up. So the answer is work done is a big fat 0. Moving on to the next question coming up on your screen. Here it is. A uniform magnetic field acts right angles to the direction of the motion of the electrons. Okay, acts perpendicular to the direction of the motion of the electrons. As a result, electron goes in a circular path. Radius is given. Speed is doubled. Radius will, how many times, what will happen? Think logically. How many times will the radius change and what will be the new radius? We all know radius is mass into velocity divided by QB. So radius is basically proportional to velocity. So think now what should happen if the speed is doubled. That means velocity is made 2 times, radius will also be 2 times. So radius originally was 2 centimeters, 2 centimeter into 2 times will be nothing but 4 centimeters, which is C for Captain Shreyas. Yep, it is option C. Very good, Pravina. Excellent. Yes, that's the correct answer. So it will become 2 times. It's just simply put directly proportional to the speed. Time period will not change just because you have doubled the speed, if that was asked. Okay, but time period is going to be the same because it is independent. It is basically independent of the speed, right? That's the idea behind it. Moving on to the next question on your screen. Electron is given, moving at a right angle is given, field is also given, time taken by the electron to complete the orbit. Direct formula and substitution. Let's see who is quick in the substitution and getting the final answer after calculation. Time period is asked. Come on. Simple. 2 pi divided by 2 pi m divided by qb. That is the formula. So 2 into 3.14 into mass of an electron is roughly 9 into 10 to the power minus 31 kg. That's the rough mass of electron. You should know it by heart, obviously. Divided by, you would know it in chemistry, right? Atomic structure. Charge is already given. That is also standard. Even if they don't give you, you know it. 10 to the power minus 19. And magnetic field is 3.53. 3.534 into 10 to the power minus 5. That's what it is. Okay. Let's do one thing. 2 goes with 1.6 as 0.8. So why not write it like this? 3.14 into 9 divided by 0.8 is 8 into 10 to the power minus 20. So it is 8 into 10 to the power minus 20. On the top, I have 10 to the power minus 31. Okay. What else? 3.534 is there. So 3.534 is there. And 10 to the power minus 5 is also there. Okay. Now observe these numbers. 9 threes are 27. 9 threes are 27. Agree? 8 threes are 24. 8 threes are 24. But 8 into 3.5 will be slightly more than 24. Agree? So maybe somewhere close to 28 because it is 3.5. So it will be exactly between 24 and 32 because 8 threes are 24, 8 fours are 32, somewhere exactly near that middle point. So it will be somewhere close to 28. 3 nines are 27. So 3.14 into 9 will be slightly more than 27, means very close to 28. Numerator and denominator, are you able to see? This is manipulation. I am not exactly multiplying. I am just thinking in my head. This will be very close to 28 and this will be also very close to 28. 28 by 28 is nothing but 1. 28 by 28 is nothing but 1. Everybody with me? Minus 20 minus 5 minus 25. Minus 31 and minus 25 cancel. What is remaining? 10 to the power minus 6 seconds, meaning it is 1 microsecond. That should be the answer. Yes, option A is the correct answer. Did you understand how I do the calculations? In the examination also I would do the same thing. I will not sit and multiply. That will be stupidity. Lot of toppers, lot of students who get above 600 marks, they exactly do this without calculation. They just roughly think, it will be somewhere more than this, less than this. So it will be approximately 2 or 3 or 4 or whatever. And they check the options. Oh, this option is the closest, mark it. You always go to the closest answer. You always go to the closest easy calculation. Makes your job easier. Understood, my dear warriors? Moving on to the next one. Charged particle moving with the speed of this much enters a magnetic field perpendicularly. Field is also given. Moves in a circular path of radius 2 cm. Charge per unit mass is asked. Okay, radius is given. Charge by mass is asked. So let's use the radius formula, obviously. Let's use the radius formula. Radius is mass into velocity divided by qb. What is asked? Charge per unit mass. So Q on the top, M below. So therefore Q divided by M will be, take R below, V is as it is on the top, V by RB. V by RB. So that's what is asked. So therefore, specific charge per unit mass will be velocity. Velocity is 4 into 10 to the power 6 divided by radius 2 centimeters. That means 2 into 10 to the power minus 2 meters. Magnetic field is 2 SI units. So 2 2s are 4, cancels 4 and 4. So 10 to the power 6 divided by 10 to the power minus 2 will be 10 to the power 8 coulombs per kg. That should be the answer. Coulombs per kg, which is option D. D for Ames Delhi. D for doctor. Very good, Vedant D, PG Vijay, Naveen, Abhinya. Yes, that is the correct answer. Very good, guys. Are you getting confidence as you are solving these questions? Are you seeing the kind of questions which are actually asked in the NEET examination and the patterns which can be asked on these formulas? I hope that you are getting confidence, right? So let's go to the next one coming up on your screen. Particle of charge Q, mass m, moving with some speed, enters a region with magnetic field beyond x more than 0, okay? And the magnetic field is in the k cap direction. The particle penetrates in the region in the x direction up to a distance d equal to. First, let's understand. Darshan, I am very fast. Kya? No, bacha, I am very slow. Trust me. I can't get slower than this. If I go slower than this, you will sleep off. The speed is perfect. There is no hurrying. I am solving everything with explaining each and every step. Nobody will say that. Okay, this is the normal speed. Okay, if you feel that I am going fast, then you should watch the recorded class at 0.5x speed. YouTube will give you that option. Let's see this question. First of all, the particle is going along the x-axis. It enters a region with magnetic field beyond x. So just imagine that this is your y-axis, this is your x-axis, z-axis is towards you. This is y, this is x, this is minus x, this is minus y. The magnetic field is beyond x only. And where is it? Towards the z-axis, that means towards you. So there is magnetic field in this particular region. There is magnetic field in this particular region coming towards you. So I'm showing that as the magnetic field. The charged particle enters like this. This is that charged particle. It enters like this. Till this point, nothing will happen. It will continuously go in a straight line because there is no force. The moment it enters here, what will happen? It will experience a force. It will experience a force, yes or no? It will experience a force, yes or no? Now think about it. Where will the force be? Velocity is forward, magnetic field is here, V cross B. It's like asking somebody to come from behind. Do that like you do in swimming. V cross B. V is there, B is here. V cross B goes down, so the force is basically downwards. The force is basically downwards like this. That means the particle will go like this, come here, and then just straight away come out from this point. Is that right? Everybody is able to visualize this. It does a circular motion only till here. After that, no force, it just comes out straight. Just similar to a problem which we solved some time back. So now think, my dear students, if you read the question, you will get to know what has been exactly asked. How deep in that region will it penetrate? How much will it go inside that region of that particular magnetic field? How deep inside is it exactly going? Come on, think about it. The magnetic field is everywhere over here. How deep is it going? Meaning they are just asking you, what is this distance? What is basically that distance? Isn't that distance actually equal to the radius? Isn't that distance actually equal to the radius of the circular motion? And the radius formula is nothing but mv by qb, which is option B. That's it. So the question was very lengthy, was very nice, imaginative, but there was not even one single line I wrote because it was not needed. It was pure visualization. You have to take, rough space will be there in the NEET book. You draw this diagram in the NEET book, you understand the problem, then you realize, oh, what they are actually asking is the radius. I know the formula of radius. You're not even going to bother writing it. You are just see the options, mark it as mv by qb. That's how it is. Is that clear? Minus, if it is there, Akib, yes, it will go on the top. Yep, obviously. Is that clear? Everybody with me? Awesome, awesome, awesome. Let's move ahead to the next concept where both electric and magnetic fields are there together. Both electric and magnetic fields are there together. Now, just imagine this example where there is magnetic field like this, okay, and let's say there is electric field also like this. Let's say I take a charged particle. Charge is Q, mass is M. I leave it from rest. It is at rest initially. What do you think will happen next? What do you think will happen next? Will it go somewhere? Will it accelerate? Will it go circular? Or something else only will happen? Think about it. Because of the magnetic field, nothing. Because velocity is zero. Because of the electric field, yes, there will be a force. And every charged particle experiences force in the direction of the electric field. So I can say there will be a force because of the electric field like this. Because of that, you will see that the particle will acquire some velocity. There will be some velocity, right? Only because of the electric field. But this velocity is parallel to B. This velocity is parallel to the magnetic field. So, can I say this magnetic field will apply no force? There will be no force on that charge because it is parallel. V cross B is going to be a big fat 0. So, whether magnetic field is there or not there, whether it is opposite or this side, doesn't matter in this case. So, you will see that the particle will have constant force only because of electric field. So that force will be the charge into the field, and we all know force is basically mass into acceleration. Therefore, using this I will get acceleration is charge into the field divided by mass, which is definitely a constant. So it accelerates uniformly. What does it do? It basically accelerates uniformly. Is that making sense, everyone with me on this? Perfecto? Understood? Clear till this point? Cool. Now what will happen if there is magnetic field like this, maybe there is electric field like this, okay, the velocity of the particle is in some weird direction, okay. Now what do you think might happen for that particular charged particle? What do you think will happen? There will be both forces, because everything is at an angle, very weird direction, speeds are also there. So because of electric field, don't you see there will be an electric force? I will call it as Fe. Everyone with me? Fe is the electric force. Also keep in mind, because of the velocity and magnetic field, there will be a magnetic force. So do V cross B, you might see that the V cross B might come out to be maybe like this. I'm just guessing. Magnetic force because of the magnetic field, which is perpendicular here as well as here. These two forces together will produce a net force. What will it produce? The net force. So basically F is the net electromagnetic force. It's the net electromagnetic force. It's because of the electric force as well as because of the magnetic force. Both the forces are into play. And this kind of force often is referred to as the Lorentz force. What is it called? Lorentz force, my dear students. Lorentz force. So that is very important. So when you have electric and magnetic fields combined together, that total force is called as a Lorentz force, the combination of electric and magnetic. So you can say that it is charge into the electric field plus here charge into velocity cross the magnetic field. If you want, you can take charge common and you can put electric field plus V cross B. So that is basically your Lorentz force. Simple. Exactly, Akib. Yep. That is the net force which I have shown over here, the resultant of both of them. Right? Everyone clear? Diagram is also clear. The construction is also clear. The theory is also clear. How we get this formula is also clear. A very special application is there for this, and I'll show that to you. I'll show that to you. Imagine there is a charged particle and it is going with certain velocity v. Okay, there is some charge q over here. Let's say there is magnetic field inside the plane of the board. Let's say there is some magnetic field inside the plane of the board like this. So this magnetic field is basically B. Because of this magnetic field, what will happen? There will be a magnetic force. B is inside, velocity is right side. B is inside, velocity is right side. So if I do V cross B, everybody take your right hand, point the 4 fingers in the direction of velocity, slowly bend the 4 fingers inside the board plane, you will see the thumb going upwards. So you will quickly notice that there will be a force acting this way because of the magnetic field. Everyone, so that force because of the magnetic field will be nothing but Q into V into B into sine of 90. Why sine 90? Velocity and magnetic field are perpendicular. Sine 90. Great. Now, what is the next thing that you will do? What is the next thing that you will do? Here, the idea is I want to study the combined effect of electric field and magnetic field, and I want to apply an electric field in such a manner that the charged particle continues to go in a straight line. I want to apply both electric and magnetic fields in such a manner that the charged particle continues to go in a straight line. That means it will neither go this way nor go this way, nor will it accelerate nor will it decelerate. That means the net force on it must be 0. That means the net force on it must be 0. So if there is a magnetic force on the top or in the upward direction, I want to cancel it out. So I will apply an equal and opposite force in the downward direction. Who will give that force? Obviously the electric field. So I will say I will apply one more force like this. This will be the electric field force. And this will come because of the electric field. That means my electric field must be in this particular direction. This is the direction of the electric field. This value of the electric force will be the value of the electric force will be nothing but the charge into the field itself. But they will cancel each other out. Because the net force is 0. Why? Because it is straight lined motion. It is a motion in a straight line. This velocity is basically constant. It is basically constant. Do you also see that this velocity is perpendicular to magnetic field and perpendicular to electric field? Electric field is perpendicular to velocity as well as magnetic field. Magnetic field is perpendicular to velocity. Magnetic field is also perpendicular to electric field. All three of them are mutually perpendicular to each other. Can I say that? Velocity is perpendicular to the magnetic field, which is also perpendicular to the electric field. Because everything is perpendicular in this case. Everything is perpendicular in this case. When it is perpendicular, it is usually called as crossed. It is crossed, it's perpendicular, right? When things are perpendicular, it's basically crossed. So that is why this is also called as crossed field. What is it called as? Crossed field. So this is a very, very interesting example where magnetic field is also there, electric field is also there, velocity is also there, but they are perpendicular to each other. The values are chosen in such a way that this force and this force cancels and the net force is 0. So the particle continues to go in a straight line. Now once this equation is written down, it's very obvious sin 90 is 1, Q and Q will cancel. So therefore from here velocity will be E by B. Now this formula is very, very important. This formula is very, very important. With this speed only, if you throw it with this speed only, then the particle will go with a constant velocity. If the speed is little bit more or little bit less, little bit more or little bit less, what will happen? This ratio will not match. You will see one of the force will be more than the other force. So the particle will not go in a straight line. It will get deflected either here or here. If this force is more, it will go here. If this force is more, it will go here. So only certain velocities will be able to reach here, will be able to go in a straight line. This is the principle of a device called as a velocity selector. Imagine I have an electron or a charge gun. This is basically a gun which shoots out different speeds. Charges moving at very, very different speeds. Some charges are moving slow, some charges are moving really fast, and so on and so forth. There is magnetic field here, and at the same time I tell you, listen, there is also electric field. And in the front I have a small opening. Directly in front of it. Rest of it is basically closed. You will see only certain speeds will be able to reach over here. In a straight line path, and those speeds which will come out from here will have a value E by B. But any speed more or less than that, you will see either it will go like this or it will go like this. Here the velocity is not equal to E by B. So I get to choose which particles come through this hole. Which particles will come through this hole by selecting the value of E and B. If I change E, suddenly I get a different speed. If I change magnetic field, I get a different speed. I can adjust this ratio and I can choose which speed comes out of it. That is why this is called as a velocity selector. What is it called? You can choose, you can select. So it is called as a velocity selector. Is the concept, the understanding, the principle behind it very, very clear? Everyone with me? Everybody with me? Yep. Okay. Is that clear? Awesome. Beautiful, isn't it? You can get to choose your speed by choosing the electric field and the magnetic field, right? So this is used in many scientific experiments. All right. So this is a theory. You should remember this formula. V is E by B. This kind of arrangement is called as a crossed field because they are all perpendicular. Perpendicular means cross. Keep that in mind. Alright, so I think with this we should be able to start solving some questions coming up on your screen. The first one is the easy question. This is just to pump you up, confidence booster, and I want to see who is a zombie, who is not a zombie. So all the non-zombies in the house, put your hands up in the air. No, don't put your hands up in the air. Just put your hands on the keyboard and start typing the answers. Is it A, is it B, is it C, or is it D? Come on. A charge cube moves in a region where electric field and magnetic field both exist, then the force on it is. Come on, the force on it is A, B, C, D. Both are there. Both forces will be there. Electric field and magnetic field. Is it this? No. Is it this? No. Is it this? Yes. The answer is B. Very good. How many of you said B? B for bananas. इका हिंदी नहीं चालो का बाबुआ अकीब इधर हिंदी नहीं चालत रही इधर अंग्रेजी में वा बोलत रही right? So Angrezi may, if you want to study, you can study over here. Hindi ma, if you want to study, go to somewhere else. Okay, let's see. Yeah, the correct answer is option B. Obviously, this is basically your Lorentz force. Moving on to the next question coming up on your screen. Particle of charge this much moving with velocity this much enters a region of magnetic field along the y-axis and electric field along the z-axis. Charge particle continues to move along the x-axis. What's the magnitude of the magnetic field? That's the question. Come on, my dear warriors. What do you think is the correct answer? Think. What will you do? Read the question carefully. It says magnetic field y-axis. Magnetic field y-axis. Electric field z-axis. Particles motion x-axis. Don't you see x, z and y? Electric field, magnetic field, velocity, all three are perpendicular. So can I say it is basically a crossed field? It's basically a crossed field. Number one. Number two, it continues to move. It continues to move. That means the velocity has been selected to be E by B only. It will be E by B only. Very good. Excellent. Awesome. So, question is, what is the value of B? B is nothing but going to be E by V. E is nothing but electric field. Check it out. It is 10 to the power 4 volts per meter. The velocity is 16, right? Into, oh sorry, that's the charge, my bad. The velocity is just 10. The velocity is basically just 10. So that's it. It will be just 10 to the power 3. So 10 to the power 3 is option A, of course. That is the correct answer, my dear students. Everyone with me? Understood? Clearo? Perfecto? Shall we move ahead? Awesome. Let's go to the next question up on your screen. If the electric and the magnetic fields are in the same direction and a charged particle is thrown perpendicular to the field, then how do you think is the motion? You need some bit of creativity and intelligence over here to solve this. Not much of equations. There is no equation as such which is required. You just draw the diagram. Treat electric field separate, magnetic field separate. Think what will happen because of magnetic field. Think what will happen because of electric field. I think you will get the answer. Alright, come on, think about it. Think. Why will the answer be negative? Answer will be positive. It's just magnitude. Don't worry about the signs so much over here. Only question is on the magnitude. Concentrate. Come on, think about it. First of all, electric and magnetic fields are in the same direction. Okay, so let's take the effect of magnetic field first. Magnetic field is like this. Okay, now because the velocity is perpendicular, what will happen because of that perpendicular velocity? It will perform a uniform circular motion. Exactly because of the magnetic field's force, right? The force will be this way, I believe. Every time it goes like that, the force is like this. So it will perform a uniform circular motion. That's only because of the magnetic field. Okay. Because of the electric field, let's think about it. So the electric field is parallel to the magnetic field. So what will that charged particle do? The charged particle will experience a force. Because of that force, there will be some acceleration. Because of that acceleration, if the speed was 0, basically it was at rest, it will have some velocity, more velocity and more velocity. Velocity increases. So we have one motion which is circular. We have another motion which is in this direction with acceleration, with increasing speed. So if you combine this with this, it's going round and round, but it is also going front. It's going round. That's its uniform circular motion. But at the same time, it is also going front. But the rate at which it goes front is changing. It's not going at a constant rate. So usually you would have thought it will go like this, right? Usually you would have thought it would go like this. No, that is not how it goes. It first goes like this, then goes like this, then goes like this. So basically the pitch increases. Why does the pitch increase? Because the velocity increases. Because the velocity increases. In the previous case 2, which we had done as theory point, the horizontal velocity remained constant. It did not increase because there was no electric field in that case. That's the reason why in that case the pitch was constant. Here the pitch won't be constant. Hence the answer is option C, Captain Shreyas. Yes. So it will be a helix of increasing pitch. You can call it a solenoid, you can call it a spring, but it's a spring of increasing distance between the coils, or a solenoid with increasing distance between the coils, whatever you want to call it. Yep. So that is helical motion with increasing pitch. Moving now to the next concept where we study about the force and the torque. This is a very interesting thing. Okay, simple question. Moving charges in magnetic field, can they experience force? Yes, right? They can experience force. We just studied that QV cross B. Can I say a current carrying wire is nothing but charges in motion? There are electrons which are moving, so charges in motion. Is that right? Everybody with me? So now I ask you, if I take a current carrying wire and then place it in a magnetic field, do you think it should experience a force? If I take a current carrying wire, inside that there are charges which are moving. If there are charges which are moving in that magnetic field, obviously they will experience force. So won't the wire as such experience force? The answer is exactly yes. So this is what now we are going to study, my dear students. If you take a current carrying wire inside a magnetic field, you will see in most of the cases experience some kind of force. Exactly. Perfecto. So let's see what is that force. And the formula goes like this. If you have a wire, okay, of let's say a length L carrying current I, okay, the length is basically L and the current is basically I, and let us say the magnetic field maybe is in this direction, then there will be a magnetic force given by IL cross B. So if the length, that is the direction of the current, is this way, cross B, length is like that, B is right side, so there will be a force like this, and this force is nothing but IL cross B. IL cross B, right? I'll just use the same color so that it's easy to see it and understand. IL cross B. That's the magnitude and the direction of that force. So this is the force on a current carrying wire in a magnetic field. Here also you will see that if I take a wire, the current, let's say, is like this, and if I take a wire, let's say the current carrying is like this. In the first case, let's say the magnetic field is in this direction. Second case also magnetic field is in the same direction, just the orientation has been changed. You will notice that in this particular case, the length and the field are same direction. So the cross product sine 0 will be 0. Cross product will be 0. Exactly. Very good. So here you will see that the net force on that wire is 0. Do not remember bill. That is nonsense, utter nonsense. Many teachers try to teach the force on a current carrying wire is bill. No, don't remember bill, because then you don't remember who is coming first, which vector is coming next. It is IL cross B, end of story. It's not Bill. Bill will work only when the angle is 90. What when the angle is not 90? What if IJK components are given? Then you need to remember okay, L comes first, then B. It's not IB cross L. No, it will give a wrong answer. So IL cross B is the way to remember it. Here, if you notice, the angle between length and the magnetic field is 90 degree. Angle between length and magnetic field is 90 degree. So, in this case, the cross product will be maximum because sine 90 is 1. And the maximum value of sine is 1. So here, you will see length cross B. Length is on the top, magnetic field is towards the right. Length cross B. Length cross B, thumb goes inside. So you will see that the force is here. This force is the maximum because sine 90 is going to be 1. That's how it works. So depending on the orientation, you will see that the force can change. Depending on the orientation, you will see the force can change. Yes. Sheena, this is a marathon. No, there will be no break because this is the last topic. After this, it's over. There will be some problems. We are going to study force and torque on loops. That's all. That's the end of the story. Now, imagine I give you a question like this. Imagine I give a question like this. There is a wire which is carrying, let's say, 2 ampere of current. Let's say the length is 4 meters. Let's say over here the magnetic field is, example, let's say 0.5 Tesla. I ask you what is the magnitude of the force given the fact that this is basically 150 degrees. Let's say this is 150 degrees. Example, some random value I have taken. So the question is, how much is the force acting on that particular wire? Okay. First, I will apply the formula. Force is basically ILB, IL cross B, but when I do the magnitude part, it will be basically just sine theta. What is this theta? Angle between the length and the magnetic field. Length is like this, magnetic field is like this. The angle has been already marked for me. Current is 2 amperes, length 4 meters, magnetic field 0.5, sine theta, that means sine 150. 0.5 into 2, 1. So basically only 4 is remaining. What do I do with sine 150? Sine 150, I can say it is basically 180 minus 30. 180 degrees minus 30. Sine 180 minus theta. Sine 180 minus theta is sine theta. All silver teacups. It's in the second quadrant. This angle is in the second quadrant. So the answer must be positive. So definitely it's positive. It's as good as saying just sine theta, which is basically sine 30. Sine 30 is basically half. So it's going to be 2 newtons. The answer is 2 newtons. Yeah. I hope this is clear. Even if you take it in radian, what difference does it make? Sine 60 is same as sine pi by 3, no? How does it matter whether you write it in radian or degree? It won't matter over here, right? So, yep, that's the correct answer. Yep. I hope this is very, very clear. Now I will give you a mind-blowing trick for solving crazy problems. Imagine a lot of students will take a long time to solve these kind of questions, but you, my dear warriors, in the NEET examination will solve it in a very simple and easy manner. Just imagine this is the kind of question that you have. Imagine this is the kind of question you have. There is a semicircular wire. There is a semicircular wire. The current carrying in it is I. The radius of it is R. And let's say there is magnetic field also, maybe, like this. Example, there is magnetic field everywhere, okay, like this. So there is a magnetic field this way inside the plane. Question is, what is the force on it? That's exactly the question. What is the force on that semicircular wire? I'll be like, okay, this is crazy problem, sir, because if you notice, each element of that wire, each element of that particular wire is in different directions. IL cross B, IL cross B, IL cross B. Every time you have to do IL cross B, and every time you do IL cross B, one force is here, 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 one force is here. So many forces. Beautiful drawing it is looking like a sun which you show in your drawing class. But the problem is, come on, think about it. You know, these directions are different. So I have to take the vector sum and then solve the problem. It's crazy. I mean, I don't like this. I have to do vector sum to find basically the net force. But I won't do that because I am going to teach you an awesome trick. And the trick is as follows. If you have basically, imagine a curved wire like this, any curved wire carrying certain current. This is your curved wire carrying current, and there is some magnetic field, maybe like this, who knows. This is the magnetic field B. What you can do is, if this magnetic field is uniform, that's very important, not for non-uniform, only for uniform. Forget the curved wire, replace it with a straight wire. With the same current. Whatever force acts on that straight wire also acts. Whatever force acts on the straight wire also will act on the curved wire. So basically the force acting on the curved wire is same as the force acting on the straight wire. Let's say the length equivalent is L, so L equivalent cross B. That is the formula for the force acting on a curved wire. Isn't it interesting? Yes, so it becomes straight. The proof of that is not important. It basically comes from law of polygon of vector addition. That is not the point of discussion over here. That is not what we are talking about. The point that you should understand is the application of this property. Wherever you have a curved wire, you can replace it with a straight wire. It's like distance versus displacement. Just draw a straight line. That's the effective length of that wire. That is the effective length of the wire. So over here, can you guess that effective length? Can you guess that particular effective length? Starting from here till here, that is nothing but the diameter. The diameter is the length. So L effective is basically 2R. So just think about a straight wire. Carrying current I, and it is placed in a magnetic field over here. So obviously it will experience force I L cross B. Length is there, magnetic field inside. So there will be a force like this. That force will be I L effective into B into sine. You can see length and magnetic field both are perpendicular, so sine 90. So I into 2R into B. So that's it. F is 2IRB. Exactly, 2IRB. Very good, Pravina. Very good, Priyanka. Excellent. Yes, that's the answer. Very good, PG Vijay. Understood? So we avoid integration, we avoid vector addition, we avoid all this nonsense. This is not required. This is utter nonsense. This is waste of time. This formula, this shortcut of effective length, where you replace a curved wire with a straight wire, simplifies the problem by a big deal, of course. Now I change the thing little bit, and what I do is I take a loop. When I say a loop, that means it starts at some point and ends at the same point. Basically, this is a loop. It could be a circle, it could be a square, who knows. This is basically a loop carrying current. Can you guess what is the effective length of this? Assuming this is placed in some magnetic field, maybe like this over here. This is a magnetic field, right? Question is, what is the effective length? Quickly tell me the answer in the chat box. I am reading your chats. Yes, the shortcut is good. Very good. What do you think is the effective length of this entire loop? You start and end at the same point. So your displacement is 0. It's just like displacement. That's what I told you. The trick is the effective length is just like the displacement. You start and end at the same point. You replace it with a straight wire of 0 length. Exactly. So L effective is basically a big fat 0. Can you guess the force acting on it? Can you guess the force acting on it? What will be the net force acting on it? I0 into B is a big fat 0. Yes, it will be a big fat 0. A very important result. A loop carrying current experiences, so there is zero net force on it in, very important, in uniform magnetic field, which is usually the case, uniform magnetic field. Very, very important property. It is a direct result of this particular property only. The force acting on a curved wire is the same as the force acting on a straight wire. This property only, I can extend it for a loop. As simple as that. Cool. Now comes the real question. Find the force on a loop is 0. The force acting on a loop is 0. But do you think the loop will not rotate? Will it not turn? I doubt that now. I doubt that. I don't think so. I'll just give a simple example. Look over here. Imagine there is a loop like this. Imagine there is a loop like this. Let's say this is breadth, or maybe this is width W, this is length L, and let's say the magnetic field is in this direction. Magnetic field is in this direction. Think logically now. Will each part of it experience some force? Please understand, this is your x-axis, this is upwards is your y-axis, this direction is your z-axis. This is x, this is y, this is z. Think logically, okay? See how the current is flowing now. Let's say the current is flowing like this, or yeah, whatever, like this. If you take this part, the right part, length is going inside, magnetic field is towards, length is going inside, magnetic field is towards your right side. Inside cross, like this cross B, check it out. Length cross B is going down. Are you seeing that? Length cross B. Are you able to visualize it? Length cross B is going down. Everyone with me? Yep, length cross B. Check this out. The current is going like this, B is like that, it will go in the minus Y direction. So can I show that the force is acting like this, and it will be current into length. Length is W into B, IWB. Everyone with me? IWB, perfecto. What about this? What about this part? Come on. Come on. I'm not really sure what is your question, Akib. What do you mean by G? G, we are not discussing gravity over here. Gravity has no role to play here. Okay, we are neglecting gravity forces in all these things. We are just talking about electromagnetic forces. So this length or this length is in the direction of B. L cross B will be 0. L cross B will be 0. So can I say there will be 0 force on this element as well as this element, everyone? This part and this part, length, parallel or anti-parallel, sine 0, sine 180, 0. What about this part? Obviously, if the current is going like this, force is like this. If current is coming this way, obviously the force must be opposite, no? The force must be opposite. It will be IW into B. Everyone with me? Everybody with me? Now don't you see, these two forces are actually trying to rotate the loop. Yes, the net force is 0. Net force, which is IWB minus IWB, is a big fat 0 because anyways it is a loop. But I don't think the torque is 0. I don't think the torque is 0. If you notice, it is trying to create a torque like this. It's like a couple force. So the torque is of a couple force. Couple means two people. Single is one, couple is two. Two people, couples. Boy and girl, opposite. Right? One this way, one that way. Opposite forces, they form a couple. So that is a couple force. And the torque produced by it is the distance between the forces distance between the forces into any one of that particular force. So what is the distance between the forces? It is basically L. The distance between the forces is basically L, right? Is basically L, I can say. Oops. It's basically L. What is the force itself? Any one of the force. It's basically IWB. It's basically I into W into B. Now observe carefully what I'm trying to do over here. This torque will be, observe carefully what I will try to do. I'll take current I will put W and L together and I will multiply it with B. Can you guess what is W into L? Can you guess what is W into L? Come on, think about it. अगेन मुझे हिंदी में वार्तालाप करना बहुत अच्छे से आता है, बट ये जो है ये अंग्रेजी चैनल है, इसलिए हम यहाँ पर इंग्लिश में बात कर रहे हैं. हिंदी चैनल्स तो बहुत है, इंग्लिश चैनल्स कोई नहीं है. देयर आर लैक्स एंड लैक्स ऑफ स्टूडेंट्स हु स्टडी इन इंग्लिश मीडियम बट दे डू नॉट हैव अ गुड इंग्लिश चैनल. We are better than many of the Hindi channels, let me tell you that. Okay, and we have come with a common goal that we want to help all the students across the country, whether it is south, north, east, west. No, it's for every student who wants to study in English, because we want to give quality education, right? Yeah, chalo, come on, let's talk about it. What is W into L? W into L is basically the area of the coil. Very good, very good. So can I say this is I into area into B? Oh, interesting. What if the coil had 2 turns? Maybe this wire, I take it around once more, the torque will become 2 times. If I take 3 turns, torque will become 3 times. If I take n turns, torque will become n times. So if this is for 1 turn, so therefore for n number of turns, can I say the torque will be I A N B, n times more? Everyone with me? Okay. Now this is when the loop is in the plane of B. But you know what, the loop can be at any angle. We'll come to that. But before that, let me tell you this IAN can be treated like one single quantity, and that one single quantity is nothing but M, where N into I into A is basically M. This M is basically called as the magnetic moment of that particular loop. NIA. Come on, think about it. Awesome. And Srinath, yes, that's what we will continue to help all the students in that particular way, and we'll also do something for Tamil speaking students who do not understand English, right? We are going to do something for you guys too. Don't worry if there are some students, but I see most of the students in Tamil Nadu, they learn in English, they converse in English. Doesn't matter how broken that English is, but you will speak in English. That's the good part, and that's why you're able to understand and gain the quality knowledge from this channel. That's the best part about it. All right, let's talk. So torque is MB. I have replaced these 3 terms IAN or NIA with a new term called as magnetic moment. Now what is this magnetic moment? Magnetic moment of any coil is a vector quantity, meaning if I have a coil like this where the current is going in this particular fashion, take your fingers of the right hand and curl it in the same direction as which the current is flowing. If this is your hand, assuming this is your hand, okay, see how the current is going. The current is going like this. So curl your fingers of the right hand in that direction. You will notice that your thumb will go in a particular direction. So if the curled fingers point in the direction of the current, the thumb points in the direction of basically the magnetic moment. basically the magnetic moment. This is magnetic moment of that coil. So it's basically like this. This is M, this is M. If the area is A, so it will be NIA. That's it. That's how I define the magnetic moment. Very, very important. Very, very important. It's a vector quantity, like you can see right over here. So it is definitely a vector quantity. Given direction is given by the right hand thumb rule. Curl your fingers in the direction of current. The magnetic moment points perpendicular to the plane of that loop, and you will see it is number of turns into current into area. So remember, this N over here stands for the number of turns, and this stands for basically the area, and obviously I is the current, no doubt about it. Can you guess the unit of the magnetic moment? Can you guess the unit of magnetic moment? N is turns, no unit, dimensionless also. I is current, A is area, so ampere into meter square. Ampere into basically meter square. So that is the unit of your magnetic moment. Is that clear? Very good. Awesome. Yes, Kirti, I'll be giving you the same. Actually, I've given you that, the timeline. I just made a video a few days back. I just made a video. Timetable, everything. Just please check it on the JE channel, Kirti. It's there in the video section. You will see it even 2-3 weeks back also. I have given one timeline, roadmap. Also last week I had made a video. Please check it out. Okay. Now, very important thing is, if that loop which you have, okay, has some current, and let's say the magnetic moment produced by that loop is like this, and magnetic field is not perpendicular, but let's say it makes some angle with that magnetic moment, then there is a torque acting on it. That torque is given as follows. There is a torque acting on it. If you notice, I have already figured out the direction of the torque, magnitude of the torque. Here the torque was M into B. And if you notice here, M is basically in this direction, basically perpendicular. If you take it, M is basically perpendicular to the magnetic field. But if it makes an angle, there will be a sine or cos thing, and in fact it is a sine component. Here the angle is 90, so sine 90 becomes 1. But when the angle is not 90, then you have to include that theta over here. So that torque technically will basically become your magnetic moment cross the magnetic field. So magnitude wise, you will put B over here, you will also put sine theta over here, you will put M as it is, this is magnitude wise, and this is just the torque. So this is the formula for torque, my dear warriors, on a loop. Torque may or may not be zero. But force will always be zero. Keep this in mind. So torque depends on the orientation of the loop. It depends on the magnetic moment. It depends on the magnetic field. Okay, everyone with me? Everybody with me on this? Understood? Clear? Perfecto. Can we move ahead? Yes, chalo. Let's do certain questions on this particular theory. So observe this. There is a rod of mass M, length L, resistance R, okay. It is made to slide with a constant speed on the rails where some current is maintained in a transverse magnetic field, perpendicular field. How much force is needed to keep it into motion? Okay, let's try to understand. First, let's draw the diagram. There are rails like this. Okay, these rails are maybe connected. You maintain some current in the rails, and there is this rod. It is moving with certain velocity. It's made to move with certain velocity. You establish a current inside this. Maybe the current goes like that, like this, and like this. So this is the current which is going inside that rails and the rod. Rod's mass is m, length is l, resistance is r. If it is needed, we'll use it. If it is not, we'll not use it. Because of that current, do you see that there will be a magnetic force? And first of all, magnetic field also I need to show. Let's say the magnetic field transverse, meaning perpendicular. So this is the perpendicular field, because this is the plane of the board. This is the plane of the board. It's perpendicular to the plane of the board. So that's the transverse magnetic field. So because there is current, because there is field, there will be a force acting on current carrying wires, even rods. This rod carries current and therefore it will experience a magnetic force. Use the formula: force acting on the rod due to magnetic field. I can use I L cross B. Use that formula. You will quickly realize that the force is, current is I only, length is L only, B is B only, angle between them is 90. So it is basically ILB. Which direction will it be? Length is on the top, magnetic field is inside. Length is on the top, magnetic field is inside. So if you do L cross B, take it, length up, magnetic field inside, thumb goes towards the left. So won't this force be this way? Won't this particular force be towards the left side? Isn't the velocity opposite to the force? You are moving it like this, but the velocity is basically opposite to the force. So it will retard. But it is mentioned in the question, you are maintaining that constant speed. If you are maintaining the constant speed, meaning there must be one more force, which is the external force. So the external force balances. What does it balance? Balances that force F, so that velocity is basically constant. So can I therefore say my external force will be exactly equal to F? It will be ILB only. Is that right? Everyone with me? Understood? Oh, clear? Oh, perfecto? Can we move ahead? So such a question can definitely come. They might even ask you power. Imagine they ask you the power by the external force. Power asked by that external force. It will be external force into velocity. So it will be ILB into V. That's it. That is the power which is needed to move the rod with that constant speed. Simple. That kind of question might also come. Simple. Right? Chalo. Let's move ahead. Look at this question. What does it say? It says that there is a rod, mass per unit length, lying on a smooth inclined plane, angle 30 degrees. Rod is not allowed to slide down because there is magnetic field in the vertical direction. The current in the rod to keep it at rest. Now I will allow you to take some time to think about this problem, to visualize this problem. Don't calculate anything, just draw the diagram. That's what I would say. Rod is given, it's lying on a smooth inclined plane, inclination is given, the rod does not slide down because there is current going in it and there is field in the vertical direction. So if you visualize it properly, I think you can think of it like this maybe. This is some angle, okay, this is your inclined plane, like this. Maybe the rod is like this, maybe the rod is like this, right? And maybe there's some current going in it and there is magnetic field also present. That magnetic field is like this, it's in the vertical direction. Just visualize that. See if you're able to visualize it. Yeah, this is basically your magnetic field. Think about it. And the rod is not sliding down. Interesting. So imagine the kind of forces that will be there on the rod. In fact, if you try to look at it from the sideways, it will be much better. This is the inclined plane. This is basically 30 degrees. That's what is given, right? 30 degrees somewhere. Yes, 30 degrees. The rod which is carrying current is somewhere over here. Basically, the current is going inside. So I'll put a cross. So the current is going inside. The length is basically L. magnetic field is vertical. So the magnetic field is in this direction. Magnetic field is in this direction. So because the field is here, rod is inside. So if you do L cross B, if you do L is inside. See, hold your palm like this. Make it go like this. It's in front of you like this. L cross B. First length, then magnetic field. Length is inside, field is upstairs. Length goes like this, field is like that. See, where is your right hand thumb? It is going towards the right side. So can I say that there will be a force because of the magnetic field like this? ILB. Can I say ILB will be in this particular manner? Everyone with me? Excellent. Won't this force have two components? Won't this force have two components? One component will be like this, another component will be like this. This angle will also be 30 degrees. Naturally, this will be ILB cos 30 component, and this will be ILB sin 30 component. Not just that, there will be more forces. There will be the weight of the rod. The weight will also have two components. One component of the weight will be like this, and that is nothing but your mg cos 30, right? And there will be another component like this, standard for resolution, guys. You know how to draw the free body diagram of a mass on an inclined plane. Mg cos is here, mg sin is here, and obviously there will be a normal force in this direction. Is that right? These are all the forces acting on the rod. Think about it. Are you convinced with these forces? Mg will act down. This will be mg cos, this will be mg sin. Understand that. Mg will be here. This will be also 30 degrees. So this will be the cos component. This will be the sin component. So I split that up. Now which forces will I balance? In this direction or in this direction? I think along the incline. So if you look at it along inclined plane, do you notice mg's sin 30 component is balancing ILB cos 30 component? I think I want the current. What is the current to keep it at rest? So basically, can I say current is mg, bring L and B also below, and there is sin 30 by cos 30, which I know in the next step will be tan 30. This whole thing is basically tan 30. Now you just have to substitute everything. Mass is given. Oh, mass per unit length is given. So basically m by L is given. Mass per unit length is basically 0.5. G value standard 10 divided by magnetic field is basically 0.25 into what is this? Sin 30 by cos 30 is tan 30. Tan 30 is basically 1 by root 3. So after this you can just simply do the calculations. 0.25 goes with 0.5 two times, right? So 2 by root 3 into 10. So this is basically 20 by root 3. If you put the value of root 3 as 1.73, you will get the answer. You will get the answer as 11.32 amperes. So this approximately will come out to be 11.3 amperes or something like that. Okay, so that's what the final answer is. Is that okay? Understood? Drawing FBD was important. Right hand rule is obviously important. You should be able to do cross products easily. And I'll repeat what happened. The current is going inside. Magnetic field is up. So length cross B. Length cross B goes right. That force has two components. The upward force is balanced by the weight's downward component. So mg sin is ILB cos. Mg sin is ILB cos. Rearrange to find I and substitute to get the answer. That's all. Perfecto. Perfecto. Moving on to the next question coming up on your screen, and here it is. If there is an alpha particle, okay, it's going in a circular path of radius r, speed v. This was the Ames question. Then what is the value of the magnetic dipole moment? Immediately when you look at this question, you will be like, wait a minute, how can this be a magnetic dipole moment? Then you think little bit. Okay, there is a charge particle. It is going in a circular path. If this charge particle goes in a circular path, can I say it's as good as saying there is a wire, a loop, there is a loop there is a loop and there is current in it, because current is nothing but motion of charges. Oh, so a charge going in a circular path is nothing but a current carrying loop, and that current is nothing but the charge upon the time. Charge is q, time is nothing but the distance, which is 2 pi r divided by v. So it is basically qv by 2 pi r. qv by 2 pi r, that is the value of the current of that loop. But the question is not the current, question is magnetic moment. So we all know any current carrying loop will produce a magnetic moment m, which is perpendicular to the plane, and that magnetic moment is nothing but NIA. I just gave you the formula. Here I take one time period, basically there is only one turn. Current is this, so it is QV by 2 pi r into area. What is the area of this loop? It is basically pi r square. Is this pi r square? Pi by r, one of the r goes. So I think I'm left with QV by 2, and there is r. But this is an alpha particle, that is very important. Alpha particle's charge is 2e plus 2e. So instead of q, put 2e over here. That's it, divided by 2, 2 cancel. So EVR should be the magnetic moment, which is option B. Yes, that's the correct answer. That's the correct answer. Beautiful question, right? Yes, Priyanka. Yes, Naveen. Yes, Kirtana. Yes, GLG. Very good. Understood. Clearo. Perfecto. Okay. So charge which is moving. So charge moving in a circular path. In a circular path is like a loop carrying current. Is like a loop carrying current. That is the main takeaway of this problem, because once you know the current, finding magnetic moment was never a big deal. So let's go to the next question coming up on your screen. What does it say? Coil is given at making angle 30 degrees with the x-axis. Current is I, turns are n, field is B, field is in the x direction. What is the torque experienced? All the values are given. What is the value of the torque? That's all. We know torque is mb sine theta, but the value of m, magnetic moment itself, is number of turns into current into area, and this into b into sine theta. This is a circular loop coil, radius is given, so I can further simplify this as number of turns into current into area is pi r square into b into basically sine theta. In fact, the theta is also given to me. Theta is basically 30 degrees. Now everything is given, substitute, you will get the answer. There is nothing great about this now. So number of turns is 100, current is 1, pi is pi, radius is 2, so 2 square, magnetic field is 1 by pi, and sine 30 is basically half. So many things will get cancelled. Pi got cancelled, this 2 and this 2 got cancelled. So I think 100 is there and 2 is there. So that's it. So basically it will be 200 Newton meter. 200 Newton meter is option C. Yes, that's the correct answer. Such a nice, simple, easy forward question asked in AIMS. Can you believe that? Okay. Loving these questions, enjoying these questions. Shall we go to the last part now? We'll see the final application. Okay, come on, my dear warriors. Current carrying loop is placed in a uniform field, then the torque does not depend on what? Come on. Everybody should be able to answer this JIPMER 2018 question. There is a loop carrying current in a field. Torque does not depend on. Torque is mb sine theta. So it is NIA into B into sine theta. It depends on the area of the loop. Yes. Magnetic field. Yes. Value of the current. Yes. Shape. No. So answer should be A. Exactly. Shape does not matter. Area matters, current matters, turns matters, magnetic field matters, the orientation matters, but not the shape. Clearly you can see it from the formula. All right. Now let's see the last part, like I was telling you, and that is your moving coil galvanometer. If you recollect, I have already discussed the applications of galvanometer as a voltmeter and ammeter in the previous class. There was a separate lecture: voltmeter, ammeter, galvanometer, potentiometer, basically electrical instruments. And I told you there how you can connect a resistor in series to make it a voltmeter, how you can connect a resistor in parallel, basically shunt, and make it an ammeter. So galvanometer is basically a small current measuring device. You make it into an ammeter, a large current measuring device, by connecting a shunt resistance. You can convert that galvanometer, which measures current, into an voltmeter by connecting a series resistance. That was extensively discussed with problems in the last class. Please watch it in case you haven't. Today, I'll just discuss what is exactly there inside the galvanometer, because that part needed the application of magnetism. So we had to learn magnetism first, right? Cool. So, if you look at the galvanometer, basically there are two cylindrical permanent magnets. Why cylindrical? If you notice, there is a cut in that magnet. It looks like a cylinder. It's 3D. Visualize this. This goes like that. It's like, if you combine them together, you will see a hollow cavity. It's like a hollow cavity which is a cylinder. That's why they are called as cylindrical magnets. One is the north pole, one is the south pole. Magnetic field will go from the north pole to the south pole, north pole to the south pole, north pole to the south pole. That's how it is. So basically what happens is, the magnetic field lines, all right, they go like that, all right, they go like this, they go like that, they go like this, they go like this, they go like this, they go like this. Is that right? Everybody with me? They start from the north pole, they go to the south pole, start from the north pole, go to the south pole, always, every time. Now, when the loop is like this, when the loop is like this over here, if you notice, this magnetic field is entering, this particular magnetic field is entering like this. This part you ignore because it is not touching the loop. This is outside the loop. Forget that. And finally, this part, the magnetic field is coming out like this. This part, it is entering like this, where it is touching the loop. Again, it is touching the loop here, but it is a different field line which is coming this way. Are you able to see that? So when the loop is like that, if you notice, the magnetic field which is affecting the loop is in that direction. The magnetic field which is affecting the loop here and here is in this direction. But if you notice the magnetic moment, if you notice the magnetic moment, that is basically perpendicular. That is basically perpendicular. Do you guys agree? Do you guys agree with this? Check this out. The magnetic moment is exactly perpendicular to the loop. If the loop carries some current, magnetic moment is always perpendicular to that loop. This field and this field is the field which affects the loop. So only consider that field line. When the loop turns, there will be some two field lines over there which will be affecting it. Always you will see, no matter how the loop orients, the field will be perpendicular. So technically, if you see the torque, it will be MB sine 90, which is basically MB. So the torque by magnetic field on the current coil, on the current carrying coil, is a constant, or basically I will say it does not depend. What does it not depend on? The angle theta. What angle theta it makes, it does not matter. It is always a constant. Is that clear? Okay. Now, what is this M? M is magnetic moment. What is it? NIA. So technically, this M, I can always write it as NIA. So if I pass more current in the coil, there will be more magnetic moment, there will be more torque. If I pass less current in the coil, less magnetic moment, less torque. Because of the torque, the coil will rotate. That coil is connected to a needle. That needle is just in front of a scale. If there is a lot of torque, obviously it will rotate. continuously rotates. Somebody should stop it because you have to show a reading. You have to show some value. How do you show that value? How do you make the needle stop? How do you stop that needle from moving ahead? Because there is a torque by the field, there must be something to oppose it, and that comes from a spring. That comes from a spring. Okay, so I'll repeat again what happens over here. You have the coil like this. This is the windings of that coil. Correct? This is the windings of the coil. There are magnetic field lines which go like this. They go like that. So here the magnetic field is entering this way. Some other magnetic field line, maybe from here, it came out like this. If you notice this part and this part, you can think as if the magnetic field was in this direction. You can say that because there was current in that loop, there was magnetic moment, and that is why I can say that there was a torque because of that magnetic moment. Agree? And this magnetic moment depends on the value of the current. More current, more torque. And when the coil turns, because of the torque, the pointer shifts, there will be some reading shown. There will be some reading shown. I want a galvanometer to measure current. That's the job of a galvanometer. That's what it does. It just measures the current. How do I ensure that it shows one reading? It shows one value for some value of current. Then I need to create a torque to counter it so that it stops. The needle should stop. Else that needle will keep rotating because of the torque. How will you read? How will you mark the reading? How will you measure any value? That is why you will create a torque in the opposite direction. You will create a torque basically in the opposite direction, but this torque will be because of a spring or basically a coil. It will be because of a spring or basically a coil which is getting twisted, which is basically getting twisted. When a coil twists, elasticity property, it will bring it back, try to oppose it, bring it back by restoring force. But when it twists, it creates a restoring torque. So that torque is called as the torsional torque. Torsional torque. Torsion is a word which is associated with twisting. Imagine when you extend a spring or compress a spring, if you extend it, it is pulled back. If you compress it, it is again pushed back. So there is a force which is pushing back against the deformation. When you twist something, it tries to bring it back. That torque which tries to bring it back is called as the torsional torque, or the torque of that coil or that spring which has been turned like that. That torsional torque is basically k times of theta, just like force is k times of x. Remember, spring force is kx. Similarly, the torque is some new k into not x but theta. This k is not the spring constant. It is often called as the torsional constant. What is it called? Torsional constant. This is the angular displacement. See if this is clear. Is that clear, my dear students? Now, when this particular needle is stationary, then what can you say? This torque and this torque are cancelling out each other. This torque is being balanced by this particular torque. This one is because of the magnetic field. This one is because of that coil which is there, that's torsional effect, twisting effect. Perfecto, understood, clearo, Sivakumar, understood. Now what is the torque by the coil? It is k into theta. K into theta. What is the torque by the magnetic field? Torque by the magnetic field mb, but m is nia. Torque is mb, but torque is mb. M is nothing but nia into b. That's it. That's what it is. So now just rearrange this. Just rearrange this to get the value of theta. So therefore theta will be nothing but nba divided by k. nba okay, divided by k comes below, I is remaining. So theta is directly proportional to I. Remember, I was telling you in previous lecture that the angular displacement of a galvanometer is proportional to the current. Exactly, this is how you get it. This is how you get it. And that constant of proportionality, and that constant of, just one second. Oh my god. And that constant of proportionality is basically NBA divided by K. Standard formula. Very easy to remember. I'll tell you how. NBA is football, sorry, not football, your basketball, right? NBA league. So it's a basketball. Just imagine a basketball and you are like, okay, fine, it's just a basketball. Just think of it like that. Or just think of OK. This O is like your basketball. So it is, this basketball is associated with NBA. That's the easy trick to remember. NBA divided by K, right? By the way, there is a term called as current sensitivity, which I have already told. So if the question comes on current sensitivity, it is basically the angle per unit current. So theta by I, if you shift I over here, only NBA by K will remain. So it will just be NBA divided by K. So that is your current sensitivity. It is nothing but your division per ampere or degree per milliampere or radians per ampere, whatever you want to measure it in, divisions or degrees or radians. Up to you, depending on the problem. Right? So this is the working principle of a galvanometer. There is a coil which carries current. There is a cylindrical magnet which produces a very unique magnetic field such that the field is always perpendicular to the magnetic moment. Wherever the coil turns, magnetic moment is perpendicular to the field always. And as the torque is produced because of this field on this current, the torque will try to rotate it in some direction, maybe this way or that way. It is opposed by the spring inside. The spring will create an opposite torque and it will balance it and maintain the position. So that's why you get a very unique reading for every value of current. If you change current, you will get different theta. So the torque by the coil is just like spring force. Instead of kx, it is k theta. Theta is the angular displacement. That's all. Keep that in mind. Okay, so this is the formula, like I told you, for current sensitivity, which is the deflection per unit current which passes through the galvanometer. Is that right, everyone? Awesome. So I think now we can solve some questions based on galvanometer. Here comes one question. Let's see if you guys can solve this. The sensitivity of a galvanometer does not depend on sensitivity. I just told you what is the formula for sensitivity. Theta by I is nothing but NBA divided by K. Magnetic field B, yes, it does depend on the field. Current, no, because theta by I is the sensitivity. Weak suspension, that means spring constant, that K, torsional constant. Large number of turns means N. So it depends on A, C and D. But current, it does not depend on. So hence the answer should be B. Yes, it is B. Perfecto. Okay, current sensitivity itself is angle per current. Okay, so NBA by K, that's the formula. There is no current inside that formula. Remember that. Moving on to the next question. Assertion reason type. Working of a moving coil galvanometer is not affected by the Earth's field. Reason, the field of the magnet of the galvanometer is strong as compared to the Earth's field. What do you think? Is it correct, wrong? Is it the correct explanation, or both are wrong? What do you think? Come on, think about it. Working of a moving coil galvanometer is not affected by the Earth's magnetic field. Is that so? Is that so? Yes, it is not. And why that might be the case? Because Earth's magnetic field is very weak. The bar magnets are much stronger than the Earth's field. So Earth has no or negligible effect on it. So hence both assertion as well as reason are correct. And this is also explaining it properly. Okay, so that is why you never consider Earth's magnetic field. Unless the bar magnet is only weak, then it will be a problem. Okay, now these kind of questions we have solved it previously also. I think you will be able to do it very easily. Imagine there is a galvanometer, 5% of the total current passes through it, remaining passes through the shunt. What is the value of the shunt in terms of the galvanometer resistance? Come on, think about it. You take the galvanometer of resistance G, there is some original current which is coming off I, only 5% goes inside, the remaining goes in the shunt. The remaining basically goes in the shunt. So how much will go in the shunt? 0.95 I. And how much actually goes in the galvanometer? Only 0.05 I. We all know that shunt is in parallel with the galvanometer, so that most of the current bypasses it. We all know again shunt is parallel, that means the voltage is same. In parallel, voltage is same. And what is voltage? Current into resistance. Current is 0.95 into I. Current into resistance is voltage, right? So current is basically 0.95 into I, and into resistance is basically S. Resistance is basically S. So current into resistance is the voltage here. Here, what is the voltage? This current into this resistance. That means I should just put 0.05 into I into the resistance, which is G. Now I gets cancelled. I just want the value of S, right? I just want the value of S. I got cancelled. So it is 0.05 divided by 0.95 into G. This 5 and 95, how many times? 19 times. So basically G by 19 should be the answer. Yes, that is the correct answer. Perfecto. Awesome. Awesome. Moving to the, yes, homework now. So there are some homework questions. Let's see if you can solve it. Make sure you post the answers in the comment section after the video ends. This is your first question. Take a screenshot of this. You can pause the video also. If you're watching it recorded, you can still post the answers so that I know you're watching the class even when it is recorded. Okay, maybe you missed the live class or something. I want everybody to answer it. And this is your second question. Guys, if you don't comment, I'm not conducting the next part 2. If you don't comment, I'm not conducting the next part 2. I want lots and lots of comments, not 5-6 comments, lots and lots of comments. I'm going to see, okay, or else next week I'm not scheduling the part 2. Keep that in mind. So this is your second question. Solve this also. All right, we'll do the part 2 in the next week, in the coming week. We'll be discussing Ampere's law. We'll be discussing Bart-Savart's law and solenoid, toroid, all these geometries, all these things, forces between two wires. All those things are going to come in the next class. Okay, so for today this much is enough. We have studied the effects, we have studied forces on charges, forces on currents, torque on loops, galvanometers working. These are the basic effects of the magnetic field. Okay, so I hope you enjoyed, you learnt a lot, and let me know in the comments. That's the only way I will get to know, right? And make sure you are smashing the like button. You also stay subscribed. Remember, in the description box there is a link for joining the Energized batch. Remember, Avenger batch entries are closed. It's invalid now. You cannot join Avenger batch. Energized batch, last few days, the entries will close very soon. So make sure you are a part of the Energized batch. You get the DPPs, you get the assignments, you get live classes with recordings, you get the notes, dedicated group, my mentorship. You also get test series, you get revision, everything. It's a full-fledged batch. There is nothing that you will ask for more apart from this batch to crack NEET examination. And this batch is valid till NEET 2024, May 2024 examination. Keep this in mind. So I want you to join the batch as soon as possible. Whatever classes you have missed, you can cope up with a revision backlog plan, which I can tell you separately. But remember, the more you delay, the more, back or behind you are going. There's a lot of students who have already joined and studying under me. And I want you guys to not fall back. So make the best use of it. check out the link which is there in the description box. All right, so thank you very much. I hope you enjoyed. Have a great time. Happy weekend, happy week. Captain Shreyas signing off. Hasta la vista. Bye bye. Take care.